Well, thank you. Good afternoon, ladies and gentlemen. Today I want to give you an overview about the development of this dry slag granulation pilot plant at Fenzl in Linz. In the second part of my presentation, I will show you product analysis of dry slag granulate, what we have done together with the company Loesche, formerly known as mill manufacturing company, and University of Weimar, who has done the product analysis of the slag. So why dry slag granulation technology? So we started in the end of 2010. There is a worldwide blast furnace slag production of up to 400 million tons per year with a temperature of up to 1,500 degrees. This means we have a lot of energy potential that is currently unused with the well-established wet granulation methods. So the decision was done to develop dry slag granulation technology with the selected rotating disc technology. Oops. We have set up following main objective what we want to cover with the dry slag granulation technology. The first point is the slag product quality. Generally, we wanted to make it comparable to the current wet granulated product. This means we want to have high cement qualities. Second objective is we wanted to do with this technology an environmental improvement. This means we want to have no sulfur gas emissions, and we have no or nearly no water consumption and no water contamination with slag. And the last point, as I already mentioned, is the energy efficiency. Main goal of this technology is to recover this high temperature potential of the slag and producing, for example, superheated steam or electricity generation. This is our project, how it's set up, the development. It's divided into three phases. Phase one we have already completed. Phase one was a technical plant at University Leoben. There we melted up slag up to 500 kilograms. Granulated this with the rotating disc method with flow of up to 60 kilograms per minute. The granulator had a size of 2 meters, and this was the phase where we had proven that it's possible to granulate blast furnace slag with a rotating disc method with an in-housing and producing, beside good quality of granulated product, also high temperature of gas, what will be usable for energy recovery plants. We are now in the project phase 2, so after successful completion of project phase 1, we decided together with our project partner Fenzl in Linz to build up a pilot plant. This pilot plant is much bigger than the technical plant, so we are speaking about plant with a main process diameter of 6.5 meters, and it was designed to cover a slag flow of up to 2 tons per minute. So we are currently in this stage where we are doing tests with this pilot plant at Fenzl. So main goal in the next years is to finish this project phase 2 successfully, to have the experience and the knowledge to build up or to come into phase 3. Phase 3 means we want to build up with the customer size a full-scale plant, so a dry slag granulation plant that can cover the full slag flow of a blast furnace with installed waste heat recovery system. So on this slide you can see the pilot plant set up at Fenzl. So we are directly connected with our pilot plant at the cast house floor at the blast furnace. It is designed to handle up to 2 tons per minute slag flow. At this project phase, as I mentioned before, there is currently no waste heat recovery installed, so we release the hot air into the environment. This pilot plant was commissioned in June 2017, and we're till now operating this plant with several test trials per year with an interruption in 2018 where there was for a half year the relining of the blast furnace A. On this slide you can see the schematic concept of the pilot plant. As I mentioned before, we are directly connected to the blast furnace. This means slag and iron is tapped, the slag is coming into the slag runner and flows directly onto the center of our granulator. The slag is poured on a rotating disc, so the slag is wetting the disc, will be accelerated and falls apart into fine particles at the edge of the disc. The disc impacts with high velocity on a water-cooled wall, where it falls down into the granulate bed. The whole process is cooled in counterflow method by air. So we have here a process air fan with an electric power of 1.5 megawatts that blows in air at the bottom of the granulator. The granulate bed will be fluidized and the air will be heated up and will be released to the environment. The granulated particles will be discharged at the bottom and has temperatures up to 500 degrees Celsius. Next slides, I will show you some impressions of the pilot plant. So here you can see the cast house floor of the blast furnace A. This is our, let's say, research development plant. So we extended the slag runner and guide the slag directly into the granulator. On the right hand side, you can see the cyclone dedusting system and the air blower. This is a picture of the bottom of the granulator. On the right hand side, there is the discharging system where the granulate will be emptied into the granulate box. On the left hand side, there is the cyclone dedusting system. On the right hand side, you can see our huge air blower for the plant. On this video, you can see an impression of our fluidized bed, how it's operated in the granulator. So this is just a cold operation of the plant. In the middle you can see, we call it the cup tower, where the rotating disc is located and where the slag will be poured on. So this is the location, the fluidized granulate bed, where particle will fall down and will be where the main cooling happens. On this slide you can see some impressions of the slag feed, of the blast furnace slag to the granulator. So starting here on the left side, you can see this is located still in the cast house floor. So this is the place where we divide the slag to our granulation test facility. You can see here a block inserted in the runner. This is the reason why, because we cannot take the full slag capacity of the blast furnace. So we have to reduce the slag to the desired slag flow for our test operation. On the second picture you can see the last branch of the slag flow, the slag runner just before the granulator. So this is the last chance where we can divide the slag into an emergency pit in case we have some problems with operation of the granulator. In the third picture, this is a view just before entering of the slag into the hole where it will be then poured into the granulated disc. Here I can show you a short video or impression of the dry granulation process, how it will be operated currently and the test trials. So here in the center there is the disc where the granulation process actually happens. So the particles are flying with high velocity into the water-cooled wall where it impacts and fall down and into the granulate bed, where it cannot be seen here because it's too dark down. So, having a closer look at the granulation process itself, we have made here a video zoomed to the edge of the granulator disc. So you can perfectly view here the granulation principle. We have here the rotating disc with the slag film on it. The slag film breaks up on the edge into several ligaments, and the ligament itself breaking up in a certain circumference into the small particles, what we are saying is the dry granulated slag. Having an overview on the main process parameters of a typical trail, what we are doing with this plant. So we are starting at least at cold condition. That means the granulate bed is in cold condition and have to heat up. You can see here the gray line is the process airflow. So we have here a process airflow of about 150, 170,000 standard cubic meters per hour through the plant. A blue line is the slag flow, what we calculated in the process. So you can see here we are from 0.4 up to 0.7 tons per minute into the granulator. And the orange and black line shows the temperature of the granulate bed and the off-gas temperature. So you can see here you're starting the process cold. You need a certain time of 10 to 15 minutes to heat this process up. And what we have done here, for example, in this trial, so we reduce the airflow after 40 minutes of operation to increase the off-gas temperature and the fluidized bed temperature to maximize the off-gas temperature for heat recovery application. This table shows all the tests summed up what we have done till now, so the last 1.5 years. So at least we have done 35 trials. Means granulation duration sum of over 1,000 minutes with an average granulation time of 30 minutes. We have granulated in this time over 500 tons of slag with an average slag flow of half ton per minute. We reached temperatures in the off-gas and in the fluidized beds up to 450 degrees Celsius. At the bottom of the slide, I'd like to show you the thermal power balance, average thermal power over such a trail. So on the left side you can see the thermal input into the plant, so that means generally the slag with the temperature of over 1,400 degrees Celsius. On the right side you can see the output, what you can get out of the plant. So the green piece is, let's say, the most important piece for us because this is the process air output. This means with this process, the green part, we can do energy recovery afterwards. These small parts means it's the cooling water, the violet part. So as I said before, we are impacting with very hot slag and water-cooled balls, so we extract there a lot of energy. The blue part is we are operating this plant batch-wise, so we're starting in cold conditions, so the granulate bed start as, let's say, 50 degrees. After the end of the trial, we have 400 degrees. So this part is the energy we need to heat up the granulate bed, and the red part is the energy that's still in the granulate when we discharge the granulate. So we have a temperature up to 500 degrees at the discharge. Summarizing the pilot plant operation, so we have still a lot of aims and goals to take, so we need to do further optimization, especially at the rotating disc. So we are doing research, especially on the disc design. That means geometry, different materials, cooling principle. We want to maximize the slag flow so that we know we have here this plant size of 6.5 meter diameter, and we can handle this maximum of slag flow. So we speak about a little bit over 1 ton per minute we hope to get. We want to maximize the off-gas temperature. This means high off-gas temperature means, of course, high energy efficiency with recovery methods. Yeah, at the end of the day, we have to say we want to be ready to gather so much experience as possible to be able to build up an industrial design plant that can handle the full slag flow of blast furnace. So I'm coming now to the second part of my presentation. The second part, I want to show you the product investigation, what we have done for the dry slag granulate together with company Loesche and University of Weimar. Generally, what I want to say, we always compare dry slag granulate with the current established wet granulated slag route. So we want to achieve similar quality as the wet granulated slag. So we also want to grind up the dry granulated slag and use it for the cement industry. So what we have done here, or what I want to say first, we're starting the plant sometimes with, let's say we call it pre-filling. This means we fill in wet granulated slag into the granulator, and then we mix it up with trials with dry granulated product. This means we have a probe where we have done this investigation that it's not 100% free of wet granulated product, but the calculation says it must be far above 90% of dry granulate concentration. On this slide you can, the first view, you can see the largest difference of dry granulate compared to wet granulate. So this means we have here a different shape. Means we have a round shape. We have a very smooth surface compared to the wet granulated slag. The first, what you would do with the granulated slag, you have to grind it up. Therefore, company Loesche have done grinding tests. So we also compared with the grinding test the dry granulated product with the wet granulated product. As you know, the grinding efficiency is increasing with higher moisture content, and normally if you have wet granulated slag, there is, depending on the storage and on the dehydration of the product, you still have a lot of moisture contents, up to 10% into the slag. On the other side, we have here now our dry granulated product, so with nearly 0% of moisture. So what we have done for the grinding test, we also put some water to the dry granulated product, but we also have dried the wet granulate to have a good comparison of these two products. Yeah, the result says there is nearly no difference between the dry granulated and the wet granulated product in specific power consumption when it will be grinded. Also have done different product fineness. Coming to the next analysis, this is the glass content. Glass content is a very popular factor that will be often used for the quality of granulated blast furnace slag. The blue rows are the wet granulated slag. The yellow rows are the dry granulated slag. You can see it if you build an average of these values and these values that we have a remarkable difference between the dry and the wet granulated slag. It can be explained, I think, with that the wet granulated slag will be much more rapidly cooled than the dry granulated product. So in this dry granulation process, we need much more time to become below the transformation point. We have done also cementage tests, so we have done different ratios of clinkers and dry granulated product cement mixtures. One of the results is the water content, so there's no remarkable difference, and another result is the solidification time when it starts and when it ends. There's also really no difference. The most important point, of course, for the cementers tests is the compression strength test. So we have done many mixtures of dry granulate with clinker and also wet granulate with clinker to compare each other. So we have done a mixture with the SAM 3A cement, we have the SAM 3B and the SAM 3B cement, so with the different ratios and contents of dry granulate or wet granulate in the product. And also the cement mixtures with different fineness of the product. Summing up all results of the compression strength, we have seen no significant difference in wet granulated slag and dry granulated slag. So summing up all 45 measuring points, what we put together, so the difference is nearly 0%. Maybe somebody listened carefully to Mr. Janberg's presentation yesterday. FEHS is also doing some cementers tests for us for dry granulated products. So just make it shortly. At the test at FEHS, they have found out that we have slightly minor compression strengths compared to wet granulation, but there are still investigations going on to find out what's the reason for this difference in the product analysis. Yeah, and finally, short diagram about the hydration heat. You all know high ratio of blast furnace granulated product in cementers means low hydration heat, of course lower compression strength. But between the two different products of dry and wet granulated slag, there can be no difference noticed. Last slide now, I want to give you an impression how an industrial installation with heat recovery system can look like. Thank you for your attention.
Thank you, Thomas, for a very interesting presentation and for taking us even further into the realms of dry slag granulation, and we look forward to hearing some more results when you get through to your final plant, which is not a pilot plant but a real industrial scale plant.
We have to do still some research work or development to come to the point where we will be able to build up an industrial scale plant. So
when do you think that might take place?
That's a really good question. Yeah, if everything runs well, maybe we're half year, 1 year at the point. But
so, can we come and visit us at the Global Slag conference in Vienna next year? Next year? Oh, that's
depends on how the development are running. If they're good, you're welcome.
Okay, well, we have lots and lots of questions. Let's see if we can get through a few of them. How do you regulate the slag flow to 2 tons per minute when you are directly connected to the blast furnace?
That's a good question. So there are still investigations ongoing. We're thinking about having a slag buffer in between, but everybody who has handled slag or has experience with slag knows that it's a very difficult point. We have to do some research and some tests how to handle this best. Yeah, it's still a big open point in our development and research.
Right. Okay. Gilles asks if there's no H2S emissions. Does that mean that all of the sulfur remains in the slag?
In my experience, as I know, sulfur stays in the slag by coming with air. Yes.
Okay. What effect does that have on the final cement?
This is a good question. I don't know the exact numbers, how much sulfur will be solved within the wet granulation process, but if I have it correctly in my head, it's a very small ratio of the total sulfur content, if I'm correct me if I'm not right. So this shouldn't have any major influence on the slag product.
Okay. How much air is needed for the fluidized bed?
With our current plant, we are operating with 150,000 standard cubic meter per hour. We want to decrease this air amount a little bit because we want to get higher temperature, and what to do to get higher temperature, we have to lower the air volume flow to the granulator. So for a 2 tons per minute plant, we would be, let's say, at least at 400,000 standard cubic meters per hour.
Hence the enormous fan that you had.
Yes.
Okay, which leads us on to the question, what is your specific energy consumption in terms of kilowatt hours per ton of granulated blast furnace slag?
I have not the value here, but I can tell you we have currently with this fan about 700-800 kilowatt electrical power, what we need for 0.5 tons per minute of slag flow. So you can calculate the specific values out of these 2 parameters.
Okay, is there a possibility to run this on a continuous basis? Obviously you have been doing it on a batch process, but is there a possibility in the future to run it on a continuous basis?
At first Alpine there is no possibility because this blast furnace has 3 tapping holes, and of course the blast furnace is operated in batch process, so they are switching the tapping holes, and so we have always 50% of the time slag flow and 50% no slag flow. At other blast furnaces it would be possible if the blast furnace configuration is like that.
Okay. Are there any emissions at all from the process?
Dust.
Just dust?
Dust.
That's okay.
So we need, as it's shown here in this schematic process for industrial scale plant, of course you need a filter plant to operate an industrial scale plant.
Okay, we have time just for a couple of quick questions. What is the minimum temperature to recover energy?
It's depending on the situation. Some plants want to have superheated steam produced up to temperatures 350 degrees Celsius. Other plants want to have heat recovered by using district heating with very low temperature source. It's depending on, we set our goal that we want to achieve up to 500 degrees Celsius, so we can handle most of the energy recovery possibilities in steelwork.
Okay, so have you selected any kind of particular technology for waste heat recovery, organic Rankine cycle, anything like that?
Normally in an integrated steel plant you have steam networks available, so let's say the cheapest solution would be having an boiler after the granulation process and feeding the steam network with our additional produced steam.
Okay, because 500 degrees is actually quite a high temperature. It's a quality source of waste heat.
Yes, but as higher the temperature is, as higher is the efficiency of the steam boiler, for example. So if you have 300 degrees Celsius, you cannot extract that much energy from the air for steam production compared to an energy source of 500 degrees Celsius.
Okay, so you said that slag contains 1.3 gigajoules of energy per ton?
A little bit more depending on the temperature, 1.5 up to 1.8.
Okay, so has there been a calculation done of the total amount of energy that could be reclaimed, including waste heat recovery?
It was done, but I don't have the numbers in my head. Sorry.
Okay. Last couple of very, very quick questions. Let's make this the last question. This is another one from Gilles. Very good question. How do you maintain the fluidized bed and the discharge of the granulated blast furnace slag at the same time?
I think there are similar fluidized bed designs, for example, for power plant technologies. It's not a big point to remove slag from a fluidized bed. You can deal with overflow principles. Many different solutions are available.
Okay, well in fact we have another half dozen questions, all of them from Anonymous, but we don't have time for them, I'm afraid, so we're going to have to leave it there and thank Thomas Fenzl for his excellent presentation. Thank you, Thomas.